The allure of altered time. An introduction. Time. It's a concept that both defines and mystifies our existence. We measure our lives in its steady, seemingly unwavering progression. Seconds tick into minutes, minutes into hours, and hours into the years that mark our journey from birth to old age. Yet deep within the human spirit, there resides a profound fascination with the idea of manipulating this fundamental aspect of the universe. The notion of time travel, of skipping forward into the future or revisiting the echoes of the past, has captivated imaginations for centuries. It is a recurring theme in our stories, our myths, and even our scientific inquiries, reflecting a deep desire to transcend the linear path we all follow. This fascination isn't merely a flight of fancy, it touches upon some of the most profound questions about reality itself. What if time isn't the rigid, unchangeable constant we perceive it to be in our daily lives? What if its flow could be altered, stretched, or compressed under certain extraordinary conditions? These are not just questions for philosophers or science fiction writers. They are questions that physicists, armed with the tools of mathematics and observation, have grappled with for over a century. The answers they have found have reshaped our understanding of the cosmos in truly revolutionary ways, suggesting that time is far more pliable than our intuition might suggest. The universe is a vast and dynamic stage, and on this stage, the laws of physics play out in ways that can seem utterly alien to our earthbound experiences. When we gaze up at the night sky, we are not just seeing distant points of light, we are looking back in time, witnessing the ancient glow of stars whose light has traveled for eons to reach our eyes. This simple act of stargazing is, in a sense, a form of passive time travel. It reminds us that space and time are intricately interwoven, forming a fabric known as space-time. This fabric is not static, it can be warped and curved by the presence of mass and energy, and it can behave differently for observers in different states of motion. Understanding this interplay between space, time, gravity, and motion is key to unlocking the secrets of phenomena like the twin paradox. It reveals that the steady tick-tock of a clock on your wall is not the universal standard. Different observers, moving at different speeds or experiencing different gravitational fields, can experience the passage of time in fundamentally different ways. This isn't about perception or psychology, it's about the physical reality of time itself. As we delve deeper, we begin to see that the cosmos operates on rules that challenge our everyday assumptions, opening doors to concepts that were once relegated purely to the realm of imagination. Cosmic clocks, time's relativistic nature. On Earth, our experience of time feels remarkably consistent and absolute. A second for you is a second for me, regardless of whether we are standing still or driving in a car. Our clocks, meticulously engineered, appear to march in perfect synchrony, governing our schedules, our appointments, and the rhythm of our lives. This everyday perception has, for most of human history, shaped our understanding of time as a universal metronome, ticking at the same rate for everyone, everywhere. It's an intuitive model, born from our terrestrial environment where relative speeds are low and gravitational variations are minimal on a grand cosmic scale. This is the Newtonian view of time, a reliable backdrop to all events. However, the early 20th century brought a revolution in our understanding, spearheaded by Albert Einstein. His theories of relativity unveiled a universe where time is not absolute but relative. It is intrinsically linked to space, forming the four-dimensional fabric of space-time. One of the most startling revelations of special relativity is that the faster you move through space, the slower you move through time, relative to a stationary observer. Imagine time as a budget you spend moving through space-time. The more you spend on spatial movement, the less you have for temporal movement. This effect, known as time dilation, becomes significant only at speeds approaching the speed of light, a cosmic speed limit that nothing with mass can reach. Gravity also plays a crucial role in how time flows, as described by Einstein's general theory of relativity. Massive objects like planets and stars warp the fabric of space-time around them. The stronger the gravitational field, the more space-time is curved, and the slower time passes within that field. This means that a clock at sea level, closer to Earth's center of mass, will tick ever so slightly slower than a clock on a mountaintop. Astronauts aboard the International Space Station experience both effects. Their high orbital speed tends to slow their time, while the slightly weaker gravity at their altitude tends to speed it up, with the speed effect being dominant, causing them to age infinitesimally slower than us on the ground. These differences are usually incredibly small in our everyday lives, measured in nanoseconds or microseconds, far too tiny to notice without highly precise instruments. For instance, GPS satellites must account for these relativistic effects to provide accurate location data. Without these corrections, your GPS would become inaccurate by several kilometers each day. But while subtle in our normal experience, these principles demonstrate that time is not a universal constant. It is a flexible, dynamic quantity that is influenced by the fundamental forces and structure of the cosmos. This sets the stage for understanding more dramatic scenarios, such as the thought experiment known as the twin paradox. The Twin Voyage, a journey through space-time. Let us imagine an experiment, a thought experiment, to explore these profound ideas about time. We begin with two identical twins born on the same day, sharing the same genetic makeup and at the outset the same age. Let's call them Stella, for her stellar aspirations, and Terra, for her connection to Earth. They are young, perhaps in their early 20s, full of life and curiosity. They stand at a crossroads, one that will lead them down dramatically different paths through space-time, even though only one of them will physically leave our planet. This setup is designed to isolate and highlight the effects of relative motion on the experience of time itself. One day, Stella embarks on an extraordinary journey. She boards a technologically advanced spaceship, a vessel capable of achieving speeds that are a significant fraction of the speed of light, say 80% or 90% of that ultimate cosmic speed limit. Her mission is to travel to a distant star system many light years away, explore it briefly, and then return to Earth. This journey will take many years as measured by clocks on Earth, due to the vast interstellar distances involved. As Stella accelerates to her cruising speed, the universe outside her viewport begins to look very different, and unbeknownst to her in the moment, her personal clock starts to tick at a different rhythm than Terra's. Meanwhile, Terra remains on Earth. She continues with her life, pursuing her career, forming relationships and experiencing the normal passage of years as dictated by Earth's rotation and its orbit around the Sun. She celebrates birthdays, watches seasons change, and observes the world evolving around her. From Terra's perspective, Stella is the one who is on a long, fast journey through the cosmos. Terra will feel the decades pass, her hair might gray, wrinkles may appear, and she will accumulate a lifetime of experiences grounded on our home planet, always anticipating the day her adventurous twin sister returns from the stars. Aboard the spaceship, Stella's experience is quite different. Due to her incredible velocity, time for her, relative to Terra's time on Earth, passes much more slowly. Her ship's clocks, her biological processes, even the rate at which her thoughts occur, all proceed at this dilated rate from the perspective of an observer on Earth. However, from Stella's own perspective within the spaceship, everything feels perfectly normal. Her heart beats at its usual pace, movies play at their correct speed, and she ages subjectively at her normal rate. She is simply unaware without communicating with Earth of how differently time is unfolding for her twin sister far away. Reunion and revelation, understanding time dilation. After what seems like a few years to Stella, perhaps 5 or 10 according to her ship's calendar and her own biological aging, her mission is complete. She has explored the distant star system, gathered her data, and her spacecraft has successfully decelerated, turned around, and accelerated back towards Earth, again reaching tremendous speeds for the return leg. Finally, the day arrives. Stella's ship lands back on Earth, the hatch opens and she steps out, eager to reunite with her twin sister Terra, from whom she has been separated for what she perceives as a manageable span of her own life. The reunion is, however, astonishing and perhaps a little shocking. Terra is there to greet her, but she is now an elderly woman. Decades have passed on Earth while Stella was on her relativistic journey. If, for example, Stella experienced 10 years of travel, Terra might have experienced 50 or 60 years on Earth. The exact difference would depend on the precise speed of the spaceship and the duration of the journey. Terra has lived a full life, seen generations change, while Stella returns still relatively young, having aged significantly less. This dramatic difference in their ages is the crux of the twin paradox. Why does Stella, the traveling twin, age less? It's a direct consequence of Einstein's special relativity. Her high-speed travel through space caused her experience of time to slow down relative to Terra, who remained in Earth's much slower-moving reference frame. It's crucial to note that the paradox isn't a true logical contradiction, but rather a concept that challenges our intuitive, everyday understanding of time. The key element that breaks the symmetry between the twins is acceleration. Stella had to accelerate to high speeds, decelerate to turn around and accelerate again to come home, and finally decelerate to land. Terra did not experience these accelerations. This asymmetry is what makes Stella unambiguously the younger twin upon reunion. This thought experiment and the principles it illustrates have profound implications. It tells us that time is not an absolute universal tick-tock. Instead, it is a malleable dimension of our universe, interwoven with space and influenced by motion and gravity. While building spaceships that travel at such significant fractions of the speed of light remains a distant dream, the reality of time dilation is confirmed daily in particle accelerators and by the precise functioning of our GPS systems. The twin paradox opens our minds to the universe's true, wonderfully strange nature, reminding us that the cosmos is far more intricate and fascinating than we might ever have imagined from our quiet corner of it.